Hello guys, welcome back to the CCNA routing and switching video series brought to you by ABY Design and Tech. In this video, we're going to have a look at the types of IP addresses available to us. So to begin with, the first type of IP address we have is known as a unicast address. Now, unicast addresses allow for one-to-one communication, essentially one packet going to one device. So it allows for a single device to communicate with another device, and the source IP address of any IP packet is always going to be a unicast IP address, identifies a single device. So in this example, we have host 10.1.1.44, and he's communicating with host 172.16.1.22. It's going to send a unicast packet. This unicast packet flows just from the 10.1.1.44 host to the 172.16.1.22 host. Doesn't flow to any other device. Now, the next type of IP address we have is called the multicast address. Now, the multicast address is known as one-to-many. Essentially, it allows a device to generate one packet and then deliver that one packet to multiple hosts, multiple devices. And so the way that this actually works is that these devices are going to be joining a multicast group. This multicast group has been assigned a specific IP address. Now, it's up to the devices themselves to actually tell. So it's up to the end user devices, computers, laptops, to tell the network devices such as switches, routers, that it's part of this multicast group. So in this example, the devices on the right, the 172.16.1.22 device, the 172.16.4.25 device, have told their default router, have told their router in the middle that, hey, we're part of a specific multicast group. So because we're part of this group, if you receive any traffic which is destined to this multicast IP address, then please forward that over to me. So in this case, the router knows about this, and he's only going to forward the multicast traffic to the devices which are part of this multicast group. And so this is a mistake that I made in my Ethernet video when I was talking about Ethernet multicast addresses. The way that I explained it was slightly wrong. So I said that the multicast traffic is actually delivered to all hosts on the network, and only hosts which are part of that group will process it. That is not correct. In terms of actual Ethernet or multicast MAC addresses, the devices, the computers, your laptops are going to tell the switch, hey switch, we are part of this multicast group. If you receive any traffic, any frames to this multicast MAC address, send those frames over to me. And so that way, only the devices which are part of this multicast group will receive the multicast traffic. And so essentially, multicast relies on the end devices, your computers, your laptops, etc., to go and tell the switch or go and tell the router that they are part of this group and only force traffic on to them if they receive traffic destined for this multicast group. And so multicast traffic, it ignores broadcast domain. So as you can see in this example, 10.1.1.44 has generated a multicast packet, a multicast IP packet that has been delivered to not only devices within its own network, but also devices in another network that are also part of this multicast group. Now, the last type of IP address we have is going to be called the broadcast address. This is one-to-many. So it allows a device to send one IP packet, and that IP packet is delivered to all hosts within the same network. So this is the difference between broadcast and multicast. Multicast can be forwarded over to another network. If the router, so as example, this router in the middle, in the previous example, it had devices in the 172.16/16 network, which are part of the multicast group, that 10.1.1.44 was sending multicast traffic to. So because of that, it was able to then take that multicast traffic and send it over to the devices in another network. Whereas broadcast addresses, the traffic stays within the same network. So in this case, the broadcast packet was generated from 10.1.1.44. It's only going to flow to devices in the 10.1.1.0/24 network. It's not going to flow to devices over in the 172.16.0.0/16 network. That is one of the jobs of a router. One of the jobs of a router is to stop broadcast from moving from one network to another network. Now, IP gives us 32 bits to play with. That's the number of bits in an IP address, and that gives us around over 4 billion IP addresses. Now, that is a massive pool of IP addresses to use. We need to have some way to organize it. And so the developers of IP back in the 1980s, I believe it was like 1981 or something, they came up with a way to organize the IP addresses. And they call this the classes of IP address. Essentially, we took our IP address space and we divided it into 5 classes. And each class of IP address was to be used for a specific reason and to meet a specific requirement. Now, the IP address space is divided up into classes for easier management. Think of it like this. A dictionary contains millions of words. However, to actually navigate a dictionary is very, very easy, essentially because all the words, if you wanted to find a word, all the words are organized by alphabetical order. And it's the same way, or the same method that we're using for IP addresses. There are so many IP addresses that we need to have some way to organize them so that it's easier to essentially find and search for an IP address. So if you want to have multicast IP addresses, you know which range to look for. If you want to have class A, class B, or class C, you know what to look for. And so there are 5 classes, class A, B, C, D, E. Class A, B, and C are used to assign out to hosts. Class D is for multicast and class E is for experimental. And the class that an IP address belongs to can be identified by looking at the decimal number in the first octet. The decimal number would tell us whether this IP address assigned to a host is a class A address, whether it's a class B or class C, or whether this multicast address is in fact a multicast address because its first octet is from within the class D range. Okay, so let's start off with classes. So class A, we know that an IP address is a class A address because it assigns the first octet has a value between 1 through 127. Okay, essentially the first 8 bits represent the network part of the address. So a class A address by default uses a subnet mask of 255.0.0.0. Remember, it's the subnet mask which tells us which part of the IP address represents the network part and which part represents the host part. All devices within the same network have to have the same network part of the IP address. Okay, and the first bit of the first octet is always set to 0. So as you can see, we have 7 zeros followed by a single 1 through 1 0 followed by 7 ones. So this shows the range of IP addresses in binary format. The first octet can be any value from 1 through 127. And there are only 128 Class A networks available. So Class A networks, they were created to support large networks. So the idea was by the original creators of IP were to have essentially a small amount of large networks which can support large amount of hosts, because you won't really be getting many large corporations or many large networks connecting to the internet, etc. So Class A networks, they give you 16,777,216 hosts per network. Now, as you can see, that is a lot of hosts per network. Now, the actual 127 range, so 127 dot anything, that is actually reserved for loopback testing. So with Class A, you really only get 1 through 126 to be used as Class A IP addresses. And so if you look at this example down here on the bottom right, as you can see that a Class A, this would represent a typical Class A IP address, 125.10.22.32, subnet mask of 255.0.0.0. Now let's move on to Class B. So Class B, the first octet in a Class B IP address has a value between 128 through 191. The first 16 bits represent the network port of the IP address, because a Class B IP address uses a subnet mask of 255.255.0.0. And essentially, Class B IP addresses, they were designed to support medium-sized networks. So as you can see, Class A was many few networks to support many few large networks, and then Class B is a good amount of medium-sized networks. There are 65,536 addresses per network, and there are 16,384 Class B networks available. Now, with Class B networks, the first 2 bits of the first octet is always set to 10. And so, no matter whether we go from 128 through 191, the first 2 bits of a Class B IP address will always have the value 10. Now, this IP address on the bottom right shows a typical Class B IP address, 170.220.22.32, with a subnet mask of 255.255.0.0. And as you can see, it's the first 2 digits of the IP address which represent the network port of the IP address. And a Class B can have IP address can have any value from 128.0.0.0 through 191.255.0.0. And so I would just like to point out that so far, as you can see, that there's organizations making everything easier. So we know that if we have a large network and we have a lot of hosts to support on that network, then we can use a Class A address. If we have a smaller network but still pretty large, then we can use a Class B address to support that network. And as you probably have guessed, Class C has the first octet has a value between 192 through 223. And the first 24 bits represent the network part of the IP address, because it uses a subnet mask of 255.255.255.0. This allows for over 2 million Class C networks available, but only 256 addresses per network. And as you can see, Class C, they were created to support smaller size networks. So as you can see, Class A, larger networks, Class B, medium-sized networks, Class C to support smaller size networks. And so as you can see, each class of IP address is created for a specific reason and to support different requirements. So as you can see, Class C was created to support these smaller businesses who may not have a large network. Class A to support your larger corporations who are going to have a much larger network than a local business or than a smaller business. So with Class C, the first octet can have the first 3 octets can have a range from 192.0.0.0 through 223.255.255, because essentially it's the first 3 octets of the IP address which represent the network port. And with Class C IP addresses or Class C addresses, the first 3 bits of the IP address is set to 110 of the first octet. So no matter whether you go from 192 to 223, the first 3 bits always remain 110. And the example on the bottom right of the screen shows a typical Class C IP address, 200.220.22.32. And as you can see, the subnet mask is set to 255.255.255.0. The first 3 digits of the IP address represent the network port of our IP address, and all devices within that network have to have the first 3 digits of 200.220.22. Now let's move on to Class D. So Class D addresses are reserved for multicast traffic, and a Class D doesn't have a subnet mask. And Class D addresses are not supposed to be assigned to an individual host, but instead are supposed to be assigned to a multicast group. And as you can see, multicast traffic, essentially what that does is that it allows multiple hosts to join a group, and any traffic destined to the multicast address to the group will be received by all hosts which are part of that group. Now the first octet can have any value between 224 through 239. And the first 4 bits of a Class D IP address are always set to 1110. Okay, now the Class D address range is from 224.0.0.0 through 239.255.255.255. Some typical Class D addresses or some typical multicast IP addresses you may see are 224.0.0.5, which is used for OSPF, and 224.0.0.10, which is used for EIGRP. Again, these are our routing protocols, which we will get to later on in this training course. And then lastly, we have Class C. So Class C is a set of IP addresses or a range of IP addresses that are reserved for experimental purposes only. There's no subnet mask. They're not really used at all, to be honest. The first 4 bits are always set to 1111. So because it runs from 240 to 239. And the address range is from 240.0.0.0 through 255.255.255.254. Okay, so yeah, so that was actually a mistake. It shouldn't be from 240 to 239, it should be from 240 to 255, actually. So sorry guys, that was my mistake. Okay, and then we also have some special addresses, part of the IP address range which are reserved for special purposes. So we have the 0.0.0/8, which is used to communicate with your local network. We have 127/8, so any IP address which begins with 127 is for loopback testing. So loopback testing just allows you to test the TCP/IP protocol stack on your computer. And then we also have the IP address range 169.254/16. Now this address range is used when your device cannot get an IP address via DHCP. So DHCP stands for the Dynamic Host Configuration Protocol. Essentially what that allows you to do, allows you to connect your device to your network. Your device will communicate with a DHCP server, and instead of every time you connect a device to a network, you have to statically configure the IP address or the IP settings. Your device will pick up those IP settings automatically. If for whatever reason your device can't reach that DHCP server, that server which is responsible for handing out IP addresses and IP settings to your hosts in your network, then it needs some sort of IP address to function. If you see the 169.254.anything IP address, that means that it's tried to use DHCP, it hasn't been successful, and it just picked this IP address because it needs an IP address to essentially to function and to work on the network. Now, I know what you're thinking. Wait a minute, Abda. Okay, so you've told me about the 3 subnet masks which are for the Class A, B, and C network. However, I've seen other subnet masks than the ones that you've mentioned. And I've also seen Class A IP addresses was a Class C subnet mask. So what's going on here? So the concept of classful addresses, that was created back in the 1980s. So the idea is that I don't think the actual creators of IP and essentially of the internet expected for networking to become as large as it is today. Essentially, it was only supposed to be, let's say, college campuses, small businesses, large businesses who were supposed to be connecting to the network or to the internet. Now, every single household connects to the internet. Every single household has a network. So nowadays, this rigid structure of classful addresses is not suited for today's networks. And more specifically, the subnet masks offered by Class A and B networks, they're too large. And the reason being is because you have to remember that all devices on a network send broadcasts. If we have too many devices on our network and they're all sending broadcast, then that means most of our bandwidth on our network is going to be used up by the broadcast traffic. So as a rule of thumb, it's normally recommended that you don't have any more than 500 devices in your network at the most, which are in the same network. And the problem is, with Class A, B, and C subnet masks, we have too many wasted IP addresses. Like I said before, you're never going to get a network which has got 2 million hosts, because if you had 2 million hosts in the same network, that network would be so slow because of the amount of broadcast traffic those hosts are all generating and sending between each other. Your links are going to be saturated with broadcast traffic. No traffic is going to be able to flow correctly, and you're going to have immense slowdown. So, what's the solution? The solution is to use what we call classless addresses. Essentially, we take any IP address and we give it a custom-sized subnet mask. So we can get a Class A IP address, give it a Class C subnet mask. A Class B IP address, give it a Class A subnet mask if we really wanted to. Class C address and give it a Class B subnet mask if we really wanted to. And we can actually use subnet mask in between the normal Class A, B, and C rules. So obviously Class A defines at 255.0.0.0, Class B 255.255.0.0, and Class C 255.255.255.0. We can use subnet masks in between those. And so we still use the classful concept for organizing IP addresses, but essentially we use any subnet mask that we want with the IP address. And this allows us to create networks for any size, so we can create custom sized networks. And this process is called subnetting. Now the full process of subnetting I'll cover later in a video. This is just to introduce you to the way that we essentially subnet IP addresses now, or how we create our networks now, because classful, even though you have to learn it by the book and you need to understand it for subnetting, we don't use classful address rules now because they're outdated. Essentially what we do is that we take the subnet mask assigned to that class of network. So in this case, let's use a Class A network, which is 255.0.0.0 subnet mask. Obviously that's made up of 8 bits of 1 and 24 bits of 0. And essentially the process of subnetting, all we do is that we take that normal subnet mask assigned to, let's say, a Class A IP address, and then we just steal more host bits, more 0 bits, by turning zeros into ones. And so essentially we call this a subnet, as all we are doing is breaking a big classful network into smaller networks. So think of this as a network within a network. We're taking one large network, in this case a Class A network, which gives us over 2 million host addresses, and we're breaking that into smaller networks to better suit our needs. And so let's have a look at an example of this. So in this case, let's use the Class A network 10.1.1.1. Now by Class A rules, the default subnet mask is going to be a 255.0.0.0, which gives us 8 network bits and 24 host bits. Okay, so we have one network and over 2 million hosts for that network. That's not suited for our purposes. So in this case, we have 24 host bits that we can borrow and that we can convert to network bits by just changing from a 0 to a 1. And so we would do something like this, where we would keep the IP address, but then we would change the subnet mask to, in this case, a 255.255.255.0. And so what we've done is that we've still got those 8 network bits, which were originally defined for Class A network, and then we've got 24 host bits. We've stolen 16 host bits and converted them to once, and saying that these bits now can be used for subnetting, and these bits now represent our network. And then we still have 8 host bits which can be used to represent our host within that network. Now, just by doing this, we've taken that one network and we've broken it into 65,536 smaller networks with 255 hosts per network. And that's literally just from taking this one IP address, this one class A network, this one big network, and breaking it down into smaller networks. Now, to get how many networks we've actually got available to us, all I did was take the subnet part. So the subnet part is now 16 bits long, and then just do 2 to the power 16. 2 to the power 16 gives us 65,536. So essentially, with subnetting, we're now breaking this IP address down into 3 sections. We have the network part, which was how many bits of the IP address represent the network as per the class A, B, or C rules. Then we have the subnet part. The subnet part is defined by us. This is how many bits we're borrowing from the host part in order to break down this large network into smaller networks. And so this is the magic of subnets. See, this allows us to save on IP addresses, as we can create smaller networks than the networks that are already predefined. And this allows us to meet certain requirements, such as hosts per network and number of networks needed. And you have to remember that in a corporate network, in a corporate environment, every router link needs a subnet. Every VLAN has a subnet. Every network segment has a subnet. So we can do something like this. So we can take a 172.16, so 0.0/16 class B network, and then we can subnet that down into smaller networks. So in this case, we're now using a /24 subnet mask, which is a 255.255.255 subnet mask. We've broken these networks down into smaller networks, and we're able to assign out the smaller networks to our different network segments. Now, without subnetting, in order to get the same result, we would have to basically just take multiple class B networks or multiple class C networks and assign them out to each individual link. Now we can just take one big class B network, break that down into smaller networks, and then assign them out to our different network segments in our corporate environment. And so just to run through this, as you can see, each interface on the router represents a different network. We have the 172.16.0.0/24 network over here on the left. This supports 254 usable IP addresses, 254. So essentially what you do is with subnetting, you would have a look at your corporate environment. You would decide, okay, for this VLAN, for this network segment, how many IP addresses am I going to need, and how many IP addresses do I expect, or how much growth do I expect in the next few years, etc. And you would account for all of that. So what you may typically see in a corporate environment is that you may essentially have a subnet for each office floor, or you may have a subnet for each office building. And so you would break up your network into that. And the beauty of actually subnetting, one of the massive benefits is that it limits your broadcast traffic. So in this case, the broadcast traffic for the 172.16.1 network is going to be contained to this segment. That means that if you did have a broadcast storm, which is tons of broadcast traffic on your network, which essentially brings down your network and acts as a denial of service attack, only this portion of your network is going to be affected. The other portions, these could be branch sites, these could be the main office, etc., are not going to be affected, and traffic can flow as normal. And that's it really. More about subnetting later. Again, I'll have a more in-depth video of how subnetting works. This was just kind of to introduce you to the class of networks that we have, why they originally settled on class A, B, C, D, E networks is because we have got 4 billion IP addresses. We need some way to organize these IP addresses into some sort of structure, similar to how there are millions of words in a dictionary, but we organize the words by alphabetical order, making it easier for us to actually search for a word. I hope this has been useful for you guys. If you like this, I want to see more content like this, then please subscribe to my channel and please share so that we can get high quality IT training to the masses free of charge. Thank you very much.